You know, we've all heard that story, right? Isaac Newton, sitting under a tree, an apple falls on his head, and bam, he discovers gravity. But the real story, the one we're going to get into, is actually way cooler. It's not just about why the apple fell. It's about a much bigger, cosmic puzzle that the apple helped to unlock.
So let's just start with this question, because when you really stop and think about it, it's a fantastic one. You've got the Earth, and it's right there under the apple tree, and it's also right there under the moon. So why does one plummet straight to the ground, while the other just kind of hangs out up there sailing across the sky? This was the exact paradox that got Newton's mind racing. And this was Newton's absolutely brilliant leap of imagination. He thought, what if? What if it's not two different sets of rules? You know, one for stuff on Earth and another for things up in the heavens. What if the exact same force that yanks the apple down is also reaching all the way out into space and holding on to the moon?
Now, to understand how that could possibly be true, we first have to figure out the physics of what keeps anything moving in a circle in the first place. We've got to find that invisible string.
Okay, let's start with a really simple picture. Imagine you're whirling a stone tied to a string around your head. Your hand is constantly pulling that stone inward, right? It's pulling it toward the center. But the stone doesn't just fly into your hand. It keeps moving in a big circle. Well, that inward pull has a name. It's called centripetal force, which literally means center-seeking force. And this is so important. Without that constant pull from the string, the stone would not go in a circle. The second you let go, whoosh, it flies off in a perfectly straight line. That pull is what's bending its path into an orbit.
All right, so we've got an apple falling straight down, and we've got a stone being pulled inward to travel in a circle. Now, let's see how Newton brilliantly connected these two ideas that seem totally different.
And here it is, the mind-bending reveal. The moon is falling. It's in a constant state of free fall toward the Earth, just like the apple. But, and this is the genius part, it's also moving sideways at a ridiculous speed. So as it falls toward the Earth, the curved surface of the Earth is falling away from it at the same rate. It's constantly falling around the Earth, forever missing it.
So there it is, the invisible string that's providing that centripetal force for the moon. It's just Earth's gravity. The very same force that pulls an apple from a tree is the same force that's constantly pulling the moon inward, bending its path into that perfect orbit.
Okay, but this new understanding leads to another really fascinating question. We know forces tend to come in pairs. So, if the big, massive Earth is pulling on the tiny apple, is the tiny apple also pulling back on the Earth?
And the answer is a huge yes. The apple is absolutely attracting the Earth with the exact same amount of force. But, and this is where Newton's other laws come in, force equals mass times acceleration. Since the Earth's mass is just unbelievably huge compared to the apple's, that same force barely makes our planet budge. It's an effect so tiny we could never, ever feel it. So Newton took this incredible idea that the apple, the moon, the Earth, all of them are pulling on each other, and he generalized it into this profound and beautiful law. It basically says that everything in the universe with mass pulls on everything else with mass.
Now, this law really has two main parts. The first one is pretty easy to wrap your head around. The more massive the objects, the stronger the force. Simple, right? The more stuff something is made of, the stronger its gravitational pull. A planet pulls way harder than a bowling ball.
The second part is all about distance. As you get farther away from an object, its gravitational pull gets weaker. But here's the catch. It doesn't just get a little weaker. It drops off super fast, what we call inversely proportional to the square of the distance. And when you put the whole thing together, you get this beautiful formula. The force, F, is just the masses of the two objects multiplied together, divided by the square of the distance between them. And that G? That's just a special number called the gravitational constant that makes all the units work out perfectly.
Let's make that inverse square thing really concrete. Imagine you've got two objects. If you double the distance between them, the gravity between them doesn't just get cut in half, it becomes 4 times weaker. If you triple the distance, the force becomes 9 times weaker. It fades away really, really fast.
You know, this law is also super helpful for clearing up something we get confused about all the time in our daily lives. The real difference between mass and weight. They are not the same thing.
Okay, here's the key difference. Your mass is the amount of stuff, the atoms that make you up. That number never changes, whether you're on Earth, on Mars, or floating in deep space. Your weight, on the other hand, is just the measurement of how hard gravity is pulling on that mass. Since gravity changes depending on where you are, so does your weight.
Which, of course, brings up a really fun thought experiment. We know for a fact the moon has way less mass than the Earth. So what would that actually do to your weight if you were standing on its surface?
You would weigh just 1/6 of what you do right now here on Earth. Your mass, the amount of you, is exactly the same, but the gravitational force pulling you down is 6 times weaker. And that's exactly why we see all that footage of astronauts taking those huge, bouncy leaps on the lunar surface.
But this law is about so much more than falling apples or bouncing on the moon. Its discovery was a massive turning point for humanity, all because of its incredible universal scope.
I mean, just think about it. This one single elegant law explained a whole bunch of mysteries that seemed totally unconnected before. It's why we stick to the ground, it's why the moon orbits us, it's why all the planets orbit the sun, and it even explains the rising and falling of the ocean tides. It literally unified the heavens and the earth under one rule.
This quote really says it all. It's not just about planets and stars. Right now, you are gravitationally attracting the very device you're watching this on. Yeah, the force is so tiny you could never measure it, but it is there. Every single object in the universe is part of this one big, interconnected gravitational dance. Newton's law was the very first theory to prove that the rules of physics up in the cosmos were the same as the rules down here on Earth. It showed us that the universe wasn't just chaotic, it could be understood. Which really makes you wonder, as we keep exploring all the mysteries out there, what's going to be the next great unifying idea that changes everything we think we know?